Hey guys, this is Spiral Review for Spiral number 2. We're going to start with solving some equations. First up, we've got something that involves a lot of fractions. I don't really love dealing with the fractions, so the first thing that I might do is try to get rid of all the fractions at once. And to do that, I'm going to multiply by something that will get rid of 3, 2, and 7. The common denominator of those three things is going to be 42, because 42 is divisible by all three of these. When I do that, I'm going to do this out a little bit slowly so we can see what actually goes on here. We get 42 times x minus 4 over 3. 42 times 4 is going to be 168x. 42 times a half is going to be 42 over 2. And then over here I'm going to have what really amounts to 3 over 1 times 42 over 1 times x plus 1 over 7. Okay, 42 divided by 3 is going to be 14. So we get 14 times x minus 4, which is going to be 14x minus 56. I'm going to keep my 168x. On this side, we've got 21, because 42 divided by 2 is 21. And I can reduce my 42 and my 7 to get 6. 3 times 6 is 18, so minus 18, x plus 1. So we get plus 168x is equal to 21 minus 18x minus 18. Being careful to get that negative to both pieces of this. Let's combine some like terms. 14 plus 168, 178, 182x. I'm going to add another 18, and I get 200x minus 56 is equal to 21 minus 18. Almost done here. And from this, we've got add 56 to both sides. This is really 3. So 200x is equal to 59, which means that x is equal to 59 over 200. And that's your final answer. The key here was multiplying by a common denominator at the beginning to get rid of all those fractions without having to do any adding or subtracting of fractions. The second one of these is a nested problem. So we've got this lovely looking mess of a thing that we might start from the really deep inside and work our way out and see what happens. Okay, I'm going to rewrite each one as we go, but kind of just keep this a little bit neat by only writing the stuff I'm working with. So first thing, I've got this set of parentheses, and in here is going to be x plus 3, and then that negative is going to get distributed. So we get minus x plus 1, and that's just 4, because the x's cancel out, and 3 plus 1 is 4. My next stage, we've got 2/5 x. That was minus 4. I'm going to put a 5 out in front of that and a 2x there just to figure out what's going on here. Okay. Combining things, so we get minus 5 times 2/5 x, but the 5's cancel out, and I've got 2x minus 2x, and negative 5 times negative 4 is plus 20. And in this case, my 2x's cancel out, leave me with just plus 20. I'm going to add the next layer. And at this point, we've got negative 3 times plus 20 is negative 60. That 2 out in front, and that's equal to 1. So we get 2x minus 120 is equal to 1. And that should come out to something like x is equal to 121 divided by 2. In this case, the trick was really to just kind of focus on each piece one at a time. If you wanted to, you could rewrite each line as you go. That helps keep track. I did not want to spend the time writing that for this video, so I just rewrote what I was working on and kind of kept track by keeping this under whatever it used to be. Moving on to some inequalities. We've got to solve and graph these. First thing I might want to do is combine my x's onto one side. And I'm going to be careful here because I don't end up dividing by a negative. I'll actually do this both ways. I'm going to add 7x to both sides. So we get 14 plus 4x is less than 2. Minus 14 to both sides. I get 4x is less than or equal to negative 12, which means that x is less than or equal to negative 3. Graphically, here's my negative 3, closed circle for less than, and I'm going in the left direction. If I had started this problem instead by adding 3 to both sides, I end up with 14 is less than or equal to 2 minus 4x. I might subtract 2 to both sides, and I get 12 is less than or equal to negative 4x. If I divide both sides by negative 4, I get negative 3. Because I divide by a negative, I've got to flip the sign around. The reason for that is what I'm really doing is adding 4x to both sides and then subtracting 3 from both sides. And I get, on this side, just an x. So I've got negative 3 is greater than or equal to x, which I can rewrite as x is less than or equal to negative 3, if I so desire, which is this graph. For our second inequality, what we're doing is looking at a nice double inequality, and we're going to solve these two separately. So 2x minus 1 is less than or equal to x plus 1, and x plus 1 is less than 5x minus 7. Pretty quickly for the first one, if I add 1 to both sides, if I subtract x from both sides, I get x is less than or equal to 2. And on the right side, we're going to end up getting 4x is greater than 8. And if I divide both of these by 4, we get 2 is less than x, or x is greater than 2. And I made a really fun problem that doesn't actually work because the numbers that I chose. Because we have two conflicting pieces of information. X is less than or equal to 2 and x is greater than 2. If I had chosen something that actually worked, what we would have seen is something that looks like this, where we're going for the answers between those values. In this case, we have x only can be less than or equal to 2 for the first half, and x has to be greater than 2 for the second half. There's literally no number that works because those don't overlap at all. For our first slope one, we're talking about a perpendicular bisector. That means we're looking at the point exactly in between these two. So that's the midpoint. The midpoint's going to be halfway between 3 and negative 3. 3 plus negative 3 is 0, so it's going to have an x-coordinate of 0. And halfway between 2 and negative 4, that's going to be negative 2, so the average of those is going to be negative 1. Again, to find the midpoint, I just found the average of these coordinates. Midpoint formula is the same thing. It's really not worth memorizing because you're really just talking about an average here. Now I've got to find the slope. The slope between these two would be negative 4 minus 2, which is negative 6. Negative 3 minus 3 is going to be negative 6. The slope would be 1. For perpendicular, we're looking for the opposite reciprocal, which the opposite reciprocal of 1, which is 1 over 1, becomes negative. I'm going to flip the 1s, and I get negative 1 over 1, or negative 1. Interestingly, because of the points I chose, this is going to be the y-intercept. So we can pretty happily do a y equals mx plus b equation. Y equals negative x minus 1 for that intercept. Moving on to the problems that involve finding things with k. In each of these, we're trying to find a value of k so that the slope between the 2 points is 5. I probably want to start by setting up a slope equation. So we got 4 minus 7 over k minus 1 is equal to 5. I could simplify the top to get negative 3. And what I'm going to do is multiply both sides by k minus 1. And distribute on the right, we get 5k minus 5. On the left, those cancel out, and we're left with just a negative 3. I'm going to add 5 to both sides to get 2 is equal to 5k. Divide both sides by 5 to get 2/5 is equal to k. That's our first one. For our second one, we're doing the same thing and attempting to find the same slope. So we're going to do 3 minus k, divide by k minus 2. Oh, that's a little bit different. Equals 5. And I'm going to do the same thing, multiply both sides by k minus 2 to get whatever's on the bottom out. That's a good strategy in general, to multiply by the denominator to get rid of it. On the left, we're left with 3 minus k. On the right, we've got 5k minus 10. I'm going to combine some like terms, add k to both sides to get 6k, add 10 to both sides to get 13, and when I do this out, we get k is equal to 13/6. And that works out rather nicely. Sometimes it's possible to do these graphically instead of algebraically or using a table. That doesn't tend to work well if we have fractions as our answers because we're really not good at processing that. Looking at this page as a whole in case you want the answers, we got something like this. On our second page, we're looking at a bunch of lines and piecewise functions. So these can be set up as pieces of lines instead of as whole lines, just to get us used to that. And in looking at this guy, we're starting out with y is equal to 2 plus the quantity 3x minus 1 when x is less than 1. Often we don't do well with lines that are written not in mx plus b form. So if you wanted to do that, you're welcome to. You don't have to. There are other ways around that. But we end up with y is equal to 2 plus 3x minus 3, or y is equal to 3x minus 1. We only care about this when x is less than 1, but often the easiest way for us to deal with that is to graph the whole line first. So we've got a y-intercept of negative 1 and a slope of 3. So up 3 over 1, up 3 over 1, and we end up with a line that looks something like this. What I'm going to do is to take a look at when x is less than 1. So here is where x is 1 on my line. And from this point, the only part of the line I care about is the stuff when it's less than 1. So in other words, that's the stuff on this part of the graph, or this part of this line. I don't care about the stuff that's up here. So what I'm going to do is go in and erase that. And on here I can erase it perfectly. On your paper, if you want to cross it out or otherwise identify what's going on there, that would be totally fine. I also ask you to identify any intercepts. Well, you can't really see that well, but that intercept would be 0, negative 1. The end point would be 1, 2. And the x-intercept is somewhere in there. What I'm going to have to do is solve for that. So 0 is equal to 3x minus 1. I plugged in 0 to find the x-intercept. I'm going to add 1, divide by 3. And I get the point 1/3, 0. So I've identified both the x-intercept and the y-intercept, as well as the end point. And I've taken the domain into account for graphing this thing. For the second one, I've got a more complicated piecewise function where I've got 3 different pieces. Y is equal to 2. Okay, y, oh, why are you so beautiful, Horizon? Thanks, Mr. McGillen. I know this is a horizontal line at y equals 2, so I'm going to just kind of sketch that in place now. I also know this only applies when we're between 0 and 1. Okay, so that means we're going to start at 0 and go to 1, and nothing else matters. I use two closed circles because those are both equals to, and I'm going to erase everything else. So I have this tiny little segment in here. I'm actually going to zoom in so it looks bigger because, why not? And that's really all we're talking about for that first piece. Okay, let's take a look at our next one. Again, I might write this in mx plus b form, so y is equal to x minus 1 plus 2 is x plus 1, and that's when x is between 1 and 3. So at 1 is when this graph starts. I'm going to do this one in red, just so we can see this a little more clearly. So x plus 1 means that I'm going to have a y-intercept if I was going there at 1. I'm going to go up at a slope of 1. Okay. This is only occurring between 1 and 3, so here's 1, that's my starting point. And here's 3, that's my ending point. So between those 2 points, I care about that line. Anywhere outside of there, I don't care at all. We also get an interesting thing happening where we have a closed circle and an open circle overlapping. That just means that it connects at those points. There's a point there, so we don't have to worry about that. Okay, and finally, we're looking at our last equation, y is equal to negative x plus 7. So I'm going to, again, start that as though I were graphing the whole thing, so plus 7. And then negative x is a negative 1 slope. Oh, look, it happens to connect really nicely. And at 7, I might as well stop there. I happen to hit the x-axis. So again, since we're looking between 3 and 7, and I guess that should be a closed red circle there from the previous problem, an open circle going down and ending here. Because I only care about starting at 3 and going to 7, I'm going to erase anything that I have that's before 7. I end up with a graph that looks kind of like a mini mountain thing with a little plateau on one side. And what I might do for this is just kind of make sure that everything's connected. In this case, they do connect, which is nice. And then I'm going to move on to the next part, which describe a specific situation that could produce this graph. Well, I'm going to talk about, I don't know, this looks like something starting, then going up a little bit, then going all the way down to 0. So I've got a dog pool, and the dog pool starts at 2 feet deep. After 1 minute, I add more water. And at 2 minutes, or after 2 more minutes, so 2 more, I start draining. And at 7 minutes, it's empty. Something like that would be totally fine, or anything that you'd like that makes sense. Again, I'm just going to zoom out so we can see the whole thing all together, and that's all we got.